What's up, everyone? It's trig time with Miss Wesley. Today is a big day. We get to practice finding exact values of trig functions in all four quadrants using the unit circle as a big, huge aid. We are going to start on page 17 of Trig Packet 1 at the top, where you have a unit circle that's already filled in with certain degree and radian measures that are important in the four quadrants, and we'll label it a little bit more too. We'll start things off with the joke of the day. The joke is, why were the I and the V and the X just always wandering off, wandering around? And that's because you could say that these are Roman numerals. It says, using the X and Y coordinates at points corresponding to special angles around the unit circle. Have we talked about why this is called the unit circle? Because that's very important. Think about what about this circle is a unit? And that is the radius. The radius of the unit circle is 1 unit. You may recall, and we'll get more into this when we talk conic sections, that a circle that has a center at the origin has an equation with this as the left-hand side, x squared plus y squared. It always equals the radius squared. So this turns into the equation of the unit circle. X squared plus y squared equals 1 generates this on a coordinate plane. It says now you can use, if we could fill out coordinates around the unit circle, we can use them to easily evaluate the trig functions. For these common t values, I'll talk about what t is. T is really just going to be a real number that corresponds to the angle you're falling at around this circle. So let's start with the quadrantal, shall we? Start with 0. 0 degrees or 0 radians. If I were filling in an x and y coordinate that would land me at this point, I think about the fact that this is the unit circle, right? I'm coming horizontally out 1 unit in the positive direction, and vertically I'm traveling nothing. 1 comma 0 would get me to this point corresponding to 0 degrees. What about pi over 2 or 90 degrees? Here, to get to this point, you'd have to go 0 horizontally and 1 unit in the positive direction to come up to that point up top. How about pi, the next quadrantal? So for 180 degrees, I'm coming to the right 1 unit. So I'm going to go -1 for the x. I'm going up or down, nothing. We'll have 0 for the y. And then what about my last quadrantal, 270? Let's fill this in. You're coming out 0, so 0 for the x, and then for the y, you're going down 1. Okay, keep all this in mind because I just filled out in green here, can help us get the sines and the cosines and the tangents of those special angles. But let's keep labeling. So at pi, the next one I want to tackle is a pi over 4. And pi over 4 is going to be very much related to the numbers that we end up labeling at 3 pi over 4, if you could circle that one, 5 pi over 4, and then also 7 pi over 4. So in radians or in degrees, each of these circled in red angles have a 45 degree or a pi over 4 reference angle. Pi over 4 would get me, right, the acute angle between this terminal side and the x-axis. And this diagram actually helps show this a little bit better. If I constructed a right triangle, so I went to pi over 4 at this point that corresponded to this angle, my x and my y coordinates at this point would be the exact same thing. If the radius is 1 by the Pythagorean theorem, my x and y values for this triangle would be square root of 2 over 2 twice. Well, watch what happens when we bring this over into quadrant 2. You construct a triangle of the exact same size, the exact same dimensions, but look, if we're talking sines here, well, the x-coordinate needs to be negative because you're in quadrant 2, whereas the y-coordinate stays positive. So check out 5 pi over 4, same size triangle, but you see both coordinates becoming negative, and then 7 pi over 4, something very similar. I want to get these numbers transferred over to my notes on this unit circle. So pi over 4 has x and y coordinates, square root of 2 over 2. Square root of 2 over 2, like that. Okay, sorry for the handwriting there. Can you write numerically the same two fractions? So square root of 2 over 2, square root of 2 over 2 for 3 pi over 4, but make that change in the x-coordinate. You are negative on the negative side of the x-axis, but you're still positive for the y-axis. Let's bring this down. I mean, we went horizontally this way to get to this point. Can you go straight vertically down here to, where am I going to land? 5 pi over 4 to get the same exact two coordinates, square root of 2 over 2 twice. But this time, quadrant 3, both coordinates should come out to be negative, a negative x and a negative y in that quadrant. And then we can move sideways. If I want to get myself over to 7 pi over 4, I could label the same two fractions here, so square root of 2 over 2 twice, square root of 2 over 2. But then think about the quadrant we're in now. Quadrant 4 is a quadrant where you are positive on the x coordinate and negative for your y coordinate. So negative square root of 2 over 2. And then you've come all the way around, right? Going straight up, I've completed the cycle of angles that have a reference angle of pi over 4. Next up, pi over 6. We've got some labeling to do. Let's go back to this circle. So on this circle, if I have a pi over 6 reference angle here, my triangle generated would have a radius of 1, so your hypotenuse is 1. Notice that the side opposite of the smaller angle, of the 30-degree angle, is going to be shorter. You're only coming up a half to get to this point, but over, you're going a longer distance, the square root of 3 over 2 for your x coordinate. Watch this transfer over. If I go to 5 pi over 6, which has a pi over 6 reference angle, but it's in quadrant 2, I get the same coordinates with the x being negative. You'll see something very similar for 7 pi over 6 and for 11 pi over 6, moving myself out of the way here, with the square root of 3 over 2 coming first and the 1/2 being your y coordinate. Let's try to fill that into the unit circle. So I'll switch to blue and label the x and y. So think about if you're forgetting which one comes first. Is it the 1/2 or the square root of 3 over 2? Think, man, if I'm generating this right triangle, I'm coming out further than I'm going up. So my x coordinate is going to be bigger than my y coordinate. And this should be able to be transferred straight across the unit circle over to 5 pi over 6. You'll see the same square root of 3 over 2 coming first, and the 1/2 going second, just like it was for pi over 6. But again, we're in quadrant 2, where the x coordinate needs to be negative. Let's transfer that down. 7 pi over 6. So square root of 3 over 2 and 1/2. And we're back in that quadrant 3, where both coordinates have to be negative. And last but not least, what about 11 pi over 6? So that has the same reference angle as pi over 6, same x coordinate, same y coordinate that we've been copying down in blue this whole time, but you're positive on the x and you're negative for your y coordinate there. That leaves pi over 3 and all pi over 3 reference angles around the unit circle. So pi over 3 are 60 degrees. Notice in this purple triangle, you're going out a little bit less than you're coming up. You're going out a half on the x-axis and up square root of 3 over 2. And you'll see those numbers being transferred to all 4 quadrants that we can fill in a second on our notes. So I'll try that for pi over 3. This is the one where I'm not coming out as far as I'm traveling up to get to this point. So we'll go 1/2 comma square root of 3 over 2. And then watch the signs follow how they should. Into quadrant 2, your x is now negative, negative 1/2, whereas your y stays positive, square root of 3 over 2. Bring this down to 4 pi over 3, right? You've got negative for both coordinates. So negative 1/2, negative square root of 3 over 2. And I think the last one we have to fill in, and this is a pretty labeled diagram now, 5 pi over 3, the 1/2 definitely goes first and it stays positive, but now we are down negative for the y, square root of 3 over 2. I'm going to take a second to just appreciate the beauty that is the unit circle and talk about why it wasn't a waste of our time to fill out all these many coordinates. And that's because this circle really helps us to get the sine, cosine, tangent, and all other trig functions of special angles. Let's think back to our working definition of, let's start with sine. So I'm going to write sine of theta. Well, after we went beyond SOHCAHTOA, we defined sine as the y value over the r value, over the radius. But look, we're in the unit circle. On the unit circle, r is just 1. So you can more simply define sine by just saying the sine is the y coordinate at the point you're talking about. It's y over 1. Keep that in mind. What about cosine? Cosine of theta. The same thing should happen. If we define cosine as x over r, right, and r is just 1 in the unit circle, I get to talk about cosine as just being the x value in question. And tangent. Tangent of theta's definition is not really going to shift much because we're on the unit circle. Tangent was always y over x, and it's going to stay that way. We'll keep it at y over x, and the reciprocals follow suit. So if I ask you, well, let's try one of these examples underneath. If I say go to pi over 6, Go to 30 degrees for me. And could you get me the sine, the cosine, and the tangent? Let's start with sine. So sine, I'll write sine of t, just the real number t. Well, here goes nothing. We go to pi over 6. We've got an x, a y. We know r is 1. So the sine is going to be the y value. The sine gets to just be the number 1/2. The cosine, because we're on the unit circle, so this kind of looks like cost, cosine of t. I'll go to that angle, find the x-coordinate, square root of 3 over 2. Tangent, like we said, is still going to be the y value over the x value. So tangent of t, I can divide this by that, the sine by the cosine, to get 1 over the square root of 3 or square root of 3 over 3. This is very similar to us using a table in the last lesson and just looking at these patterns. I mean, I see some of the same patterns in the circle above. A table constructed of the sine, cosine, and tangent of 30, 45, and 60 would have all fractions over 2. The cosines count 3, 2, 1, whereas the sines count as numerators 1, 2, 3. And we'll see in quadrant 1 some of those exact same patterns. Let's try the next one. It has a theta value of 5 pi over 4 is what we want to look at next. Well, to get the sine of 5 pi over 4, the sine of t, I can look to quadrant 3. I can find 5 pi over 4. And here's the x, here's the y. I can divide them for tangent. So the sine is going to be the y value, we said, and that's negative square root of 2 over 2 for this value. The cosine, I think, is going to be the same thing here, right? Also negative square root of 2 over 2, I see. Tangent, same as it always was, the y over the x. So this over that, same guy over itself, is going to equal the number 1. Quadrantals work really nicely as well. Think of, man, if I see something like theta equals pi, I'm going to think to a little tiny unit circle, and I just need these coordinates here that correspond to pi. So negative 1 comma 0 can get me actually all 6 trig functions if I really need them. How about the sine? Let's do the sine first. So sine, I'll put sine of pi instead of writing sine of t. Sine is the y coordinate. It's going to be 0. If I were asked for the cosecant, I'd have to say, oh, it's undefined because we can't divide by 0. What about the cosine? Cosine of pi. Cosine is going to be the x value, negative 1. Its reciprocal, secant, still negative 1. And then tangent. Let's see if this works. So y over x, 0 over negative 1 is certainly defined. We can call the tangent also 0. I also have some good news for you as you turn the page to 18. And the good news is no. In order to use the unit circle as a shortcut, it wouldn't be much of a shortcut if we had to fill in all those coordinates around the entire circle. So good news is that quadrant 1 values can get you values anywhere else that you need them. Good to remember where certain trig functions are positive or negative. Also good to be able to label. I mean, you don't know if the problem's going to be given in radians or degrees, so you got to be ready for anything. So I'll label 30 degrees as pi over 6, 45 degrees as pi over 4, and then 60 degrees as pi over 3. And here's your coordinates. I'm just filling in these 3 sets. So you're coming out for 30 degrees further than you're coming up. Let's put square root of 3 over 2 as your x and 1/2 as your y. And then continue the pattern. Square root of 2 over 2, and then square root of 1 over 2. So really this is just, I should just say 1/2, right? And then square root of 3 over 2 for the y coordinate. Having these, just like memorizing the table that we used in the beginning of the unit, also knowing your exact values for quadrantals, right? 1, 0, we filled this out already, 0, 1, negative 1, 0, and 0, negative 1. Should do the trick to answer any of the questions that you see below. So let's take one for instance, and we'll get plenty of chances to practice further with this. Let me try tangent of 150. So tangent of 150 degrees, step 1, draw the angle. Where does that fall? So I'd like to put it in quadrant 3, right? 150. And determine your reference angle, your theta prime. Reference angle should be what gets you over to 180, so how about 30 degrees? So let's label it. Tangent of 150 should be the same as the tangent of 30 degrees. And AS quadrant is where only sine and its reciprocal are positive. So let's make the tangent negative there. Then use your 30 degree coordinates, right? So for 30 degrees, tangent equals the y over the x. So the y is 1/2. And the x is square root of 3 over 2. That's what we want to divide. When all's said and done and the 2's cancel, we'll get negative 1 over square root of 3, or rationalize negative square root of 3 over 3. Stay tuned for the continuation of this. I will talk to you soon.